Hey, what's up everyone? I welcome you on Physics for Engineering, and today we will talk about the wheel, how the wheel works, how the wheel makes so low resistance to the motion. As we know, a long time ago, before the wheel was discovered, it was really hard to move the objects because the friction force makes really high resistance to the motion, especially for the heavy objects as on the picture. But in some point of time, someone invented the wheel, which is now the most common design feature for the vehicles, car, bicycles, and also many engineering units containing rollers and rolling elements. And what I want to investigate in this video is why such a simple mechanism like the wheel mounted on the shaft or axle makes significant reduction of the friction and force required to move the objects on the wheel. You can say that, hey, there is a bearing there with the lubrication and almost zero friction, but what about this? So obviously, in this wagon there is no bearing and probably even wooden shaft without any oil and high contact friction. Nevertheless, such a wheel still allows to move the wagon relatively easy comparing to the one without the wheel. And the question is why and how the wheel works. The donkey with wagon helps us to solve this problem. So let us assume we have a wagon with the wheel radius r capital, the axle radius s small, and with the mu friction between the axle and the wheel. We will not talk today about the rolling resistance coming from the rough rod or tie wheel deformation in the contact point. So we will consider zero rolling resistance between the wheel and rod. And this is because we will focus today on how the driving force Fd required to move the wagon depends on the wheel geometry, r capital and small, and the friction between the axle and wheel. Obviously, high friction makes high force, although our intuition says that the force must be dependent somehow on the wheel radius r capital and the axle radius as r small. So let us solve this problem and derive the exact equation for the driving force Fd. So first of all, let us define the forces acting on the axle. So obviously we will have a gravity force, mg, we will have the driving force required to move the wagon, we will have the reaction force between the axle or shaft and the wheel, and we will have the friction force. So in order to solve this problem, we need to define the coordinate system, like on the picture, and then we will write the equation for the system equilibrium. Yeah, so this we will assume that force which is moving the wagon required to move the wagon only with a constant speed without acceleration. So this means that the result of the sum of all the forces is equal to zero acting on the axle. So then we make a projection of all the forces on the y-axis, and our outcome would be this equation. So the relation between the reaction force Fr and the gravity. So this is the equation. So as the next step, we will do the same for the projection on the x direction. This will give us the following equations. So I will walk very quickly through the solution process. So if you want or if someone wants to read it, you can stop pause the video and check it more in detail. So basically the projection on the x-axis gives us the relation between the reaction force and the driving force. So now we have already the systems of two equations. But what we see in this system that we have more variables than equations so far. So we have Fr, this force which is not known, the Fd, this driving force or donkey force, and also which is not known is the alpha. So this is the angle, this is the tilting angle of the, or the direction angle of the reaction force. Therefore we need more equations. So let us then check forces acting on the wheel. The forces on the wheel will be the same as on the x actually, but in different direction. So we will have also reaction force, we will have the friction force, we will have the reaction force from the ground, and we will have the friction or stiction force, let's say, with the ground. And when we do the same procedure of projection all the forces on the x and y axis, then we will have same equations. Additionally, we will have one more equation that the stiction force is equal to the driving force. So basically we will have one more variable and one more equation. So basically we still need to have more equations to solve the problem. And yes, and the reaction force is equal to the gravity force with the opposite sign, obviously. So then as a next step we will do the following. This is our system of equation what we have, and now we need to check the torques acting on the wheel. For this purpose we will define the coordinate system which is connected with the center of the wheel, because we need a coordinate system which is moving without acceleration. And in regards to this coordinate system, we will collect all the torques acting on the wheel. So we have only two torques around this point. So this would be the torque of the friction force between the wheel and axle, and also the torque of this stiction force between the wheel and ground. As a result, we have one more equation, which is already connection between the stiction force and the reaction force. And having this equation that our stiction force is equal to driving force, now we have the missing equation number 4, which allows us to solve completely this system of equations. So we will rewrite our system from the left side, and now we start to solve this system of equations. I will walk again quickly through the solution process. So we take our driving force and put it in this equation. As a result, we have now the relations between the friction coefficient between the shaft and wheel and the alpha, this angle, tilted angle of the reaction force. So as a next step, we will divide one equation to equation number 1 to equation number 2, and as a result we have a relation between the driving force and the friction coefficient and the alpha angle. So actually these are two equations already containing two variables, and we can consider this system of equation as next solution step. So basically now we have system of two equations with two variables, and we need to solve this system. Yeah, the solution is actually a little bit complex, because we need to take the angle from this equation and put it into the equation number 1 for the driving force, because actually we are not interested in the in this angle. Yeah, it would be good to know this angle, but actually our final result, final target is to find out the dependency between the driving force and the friction coefficient, and also the radiuses, but not the angles. So how to solve this system? We will take the mu and put it in the first equation like this. Then yeah, the equation will look differently, a little bit simple, but still this is not a final solution. So as a next step for these two equations, we will do the following. So we will derive the angle from the second equation, so cosine and sine. So the relations is relatively difficult, and then we will take those parameters and put it in the first equation, so here, and this is the way how to solve actually this problem. And if we do this operation, then in the end we will have already our final result, and this is how it looks like. So this is already our final equation. So the method described above was was a little bit complex, so maybe you can find the easiest way to derive this equation, this final equation, then please write in the comments how to do that. But this is the way how I did it actually. But the final equation looks like this. So this is exactly what we wanted. So the driving force. This driving force is a function of the friction coefficient between the shaft and wheel, and also the wheel geometry, the R capital and R small. So let us then analyze this equation. So let's analyze this answer, this result. So first of all, what we can do, we can find the condition when the wheel will turn without the slipping between the rod and the wheel. Yeah, so this means that this stiction force must be lower than the slipping force between the wheel and rod, maximum slip force, which is defined by this equation. Then friction coefficient between the wheel and rod needs to be higher than this value. But this is not actually the most interesting thing. So let us investigate the special cases, I would say. So which special cases? The first of all, I would check the following condition. When our mu, our friction between the wheel and the shaft is small value, so and the mu square, we can approach this value to the 0. Yeah, and then see what does it mean for our final solution. Yeah, so if we approach mu square to the 0, yeah, then we will see that here we will have the square root from 1. Yeah, so this will be 0, this will be 0, and then our final solution will look very simple. So that we see that our driving force required to move the wheel, or we can say this is the resistance force of the wheel, will be proportional to the gravity force and proportional to the friction coefficient between the wheel and X, and also to the ratio between the axle radius and the wheel radius. And I think this already something which already looks much better than the original exact equation. So I believe we can definitely consider this approximation, because in reality the friction coefficient, especially for the modern vehicles and the modern system where we have a proper surface finish and proper lubrication, this mu will not exceed 0.1, and then mu square will be like 0.01, and then we can assume this approaches to 0, and we can use this simple equation, which is much easier to remember. So whenever we design some mechanism which contains the wheel or rollers, and we know the shaft diameter, the wheel diameter, and the friction between, we can simply calculate the force required to move the wheel, or the resistance force, which is equal to the mu mg and times the ratio between the small radius and the capital radius. Mu s, yeah, in this approximation, the condition required for turning the wheel, for spinning the wheel without the slip, will be like this. So then the friction between wheel and rod, mu s, must be higher than the friction between shaft and wheel times the ratio R small divided by R capital. I think this is a very interesting result. And the second case, so let us assume that our ratio R small divided by R capital approaches to 1. So this means that this shaft radius will be as big as the wheel radius. So basically intuition said that in this case the wheel will not work anymore. So, and we must have just a typical sliding friction, and here it is. So if we consider that R divided by R capital is 1 and checking the formula, then this will be square root from 1, here is 1, and this will be simple. Our driving force is just like mu mg, so which is absolutely correlates to the expectation. Yeah, and this is our requirement for rolling the wheel. Yeah, obviously then this friction needs to be higher than the contact friction. So this is the result, and here we have 3 cases for the following purpose. So I wanted to draw the forces acting between wheel and shaft in the real scale. From this picture, all 3 wheels have same radius but different shaft radius. Yeah, so one has a smaller radius, the second wheel has shaft radius 2 times smaller than the wheel radius, and the third one has a shaft radius almost the same as the wheel radius, so ratio 0.19. And let's now draw the forces acting on the wheel and see how they looked at in the 1-to-1 scale. So these are the forces acting on the wheel for the case where the wheel radius is 2 times higher than the shaft radius. So we see that we have the reaction force, this blue one, from the earth, or this can be also the gravity force acting on the axle. So these forces are equal. Then we have the reaction force between the shaft and the wheel. It will have this tilting angle. We will have the friction force between shaft and wheel, and we have also the stiction force which between wheel and rod, which will be equal to the driving force with different sign. So these values are already scaled. So the force values are calculated with some numbers, and these arrows, the length arrows and direction are already scaled. This is how it looks like. For the case where the shaft has a much smaller diameter, like 5 times smaller than the wheel diameter, so we see that actually our force reaction force from the earth will be exactly the same, because this is equal to the gravity force acting on the axle. But the stiction force and driving force is already much smaller. The reaction force has almost the same length and the friction force almost the same length. But nevertheless, if you now make a projections of all these forces and calculate the torques, we will see that the equilibrium condition will be met only when the stiction force and driving force will have very small value like it is. And this is actually correlates to the expectation that the smaller shaft diameter give us the smaller resistance to the motion. And for the third case, where we do expect the maximum resistance to the motion, so these are how the forces looks like. As you see, also the reaction force from the earth and reaction force between the shaft and wheel has the same value. Friction force also has almost the same value, but the stiction and driving forces already have a maximum value. This is the requirement for the system equilibrium. Here you can see the values, some numbers calculated for the numbers, and this is the reason for these 3 examples is to have some kind of feeling. So why the different shaft diameter makes a different resistance to the motion. So why the smaller shaft diameter makes resistance to the motion smaller. And the explanation would be the following. System equilibrium for the torques required that, for example, if we calculate the torque about around the contact between the shaft and wheel around this point, then we have 2 torques only. So the torque from this reaction force, this blue arrow I would say, and the torque from the stiction force. So the torque from these 2 forces will be 0 because they are going through the rotation point. And therefore this force, so this blue force, is equal for all 3 cases, and the lever arm of this force is almost equal for these 3 cases. So this is the lever arm of the blue force, this is the lever arm of the blue force, and here is the lever arm of the blue force. And this torque needs to be exactly the same, but with the opposite sign, as the torque which makes the stiction force, this black arrow. But the stiction force has already different lever arms relative to the rotation point. So for example, in this case, the lever arm is distance between here and here, so this long distance from here to here. In this case, the lever arm of this friction force is this distance, much smaller. And obviously, in order to have the same torque, then there is only way to have the same torque is to increase the force, since the lever arm is reducing. And in this case, the lever arm is very small, and in order to compensate this torque coming from the reaction force from this blue line, from the torque of the blue arrow, is to make this stiction force higher. So, and this is the explanation why actually the wheel works. So because it's about the lever arm of this stiction force. of this friction force between the wheel and the rod. So the higher the lever arm, then the smaller the friction force between the wheel and rod, and as a result the force required to move the object. So this is now we have an impression and somehow feeling how the wheel works actually. Okay, we are now back to our equation. I would like now take our result and put here some numbers, see a little bit how the result looks like on the graph if we take some real values for the wheel geometry and also for the friction coefficient for different mechanisms. Yeah, so here we have a graph. There are 3 lines, so the graph represents as the friction. So this is the actually resistance to the motion. So this value on the vertical x, this is the ratio between the driving force and the gravity force. So this is our, let's say, rolling resistance. And in this, on the x axis, we have a friction coefficient between the wheel and the x. And here we have 3 different cases. So one case when we have a wagon, with the donkey, and wagon has a ratio between the tie wheel radius and axle radius like 0.1 approximately. So then we have a vehicle like a passenger car, so obviously the radius of the wheel is already smaller, but the shaft radius is also smaller. So the shaft radius like between 30 and 40 millimeter, when the wheel radius will be like 700 millimeters, so that the ratio air divided by air capital is approximately 0.07. And here we have one more case as example is for the bicycle, where we have the smallest ratio between the shaft of the wheel and the wheel itself. This will be like 0.035. Of course, it is very different depending on the bike size, but in general this will be like this. So yeah, and here we have 2 lines. For each case we have the solid line and dot line. So basically solid line, this is the solution calculated by the exact equation, and the dot line, this is solution calculated by the approximation for the smaller frictions. So as you see that these 2 results are very close. This basically allows to use this equation for the approximation, so which is much easy to remember. So, and basically the result will be the following. So for the wagon, for this wagon with the highest, let's say, ratio, we will see that the rolling resistance has a highest value, because our ratio is the maximum. And if you consider here also the friction between the x and wheel is between the 0.2 0.3, then we will have that this rolling resistance for the wagon. For the wheel, the rolling resistance will be lower, of course, because the ratio is already smaller, and also the friction coefficient between the shaft and the wheel is already much smaller, because there is a bearing there which has a friction let's say 0.03, 0.02, therefore, so that our rolling resistance will be in a range between 3 and 4 thousandths, I would say. And the winner is the bicycle, of course, because it has the lowest ratio of the vehicle geometry between the shaft radius and the wheel radius. And considering also the low friction coefficient for the bearing, we can assume, we can calculate that the rolling resistance will be the minimum like 2 thousandths or even less. I think this is in the worst case condition. So this means that the efficiency of the rolling mechanism of the wheel on the bicycle has the maximum comparing to the vehicle or any other vehicles or wagons or whatever. So we are coming to the end, and basically the outcome will be that we can take this equation for consideration of the resistance to the motion for any rolling elements. So it's not necessary the wheel of the vehicle or bicycle. This can be any wagon. This is a support for the flowers, I would say. So this is some roller on the furniture. This is furniture as well. So any kind of rollers in the mechanism which are intended to reduce the resistance to the motion can be calculated by this equation, I believe. This can be also the shopping basket or travel bags or whatever. Yeah, okay, so this is all for today. I hope you like this video, and for the next time I'm planning to make a similar investigation to calculate the force required to move the roller with consideration of the rolling resistance between the wheel and the rod. This is something which we ignored for today's problem. So, and then there we will have a already more accurate formula for calculation of our driving force, and this could be used already to calculate the motion resistance for the complete system. Okay, so thank you for watching. If you like this video, you can subscribe on this channel. There will be many more interesting and useful investigation. Yeah, see you next time.